Thank you, everyone, for participating. This is intended to be a short webinar on some of the basic reliability capabilities in OpenSees, including basic first-order, second-moment analysis, first-order reliability methods or form analysis, as well as some basics on Monte Carlo simulation with correlated and uncorrelated random variables. And then also we'll wrap up with a finite element reliability analysis with form, or first order reliability method. So everybody see the screen that I have here?
Here on the screen I have a very simple kind of two-component reliability problem that we've all seen at some point. And basically it's a bar with a random load and a random resistance. So to kind of execute this in OpenSees, there's a few obligatory commands. Even though we're not doing in this example, it's just strictly random variables, no finite elements, but we still need to, just for reasons I don't want to go into, you still have to issue the model builder command or model basic. So it's just kind of a placeholder. You can just say model basic NDM1. It doesn't really matter how many dimensions you have, but it's just there to kind of pull in some commands and set up some other things within OpenSees. Okay, so that's first, and then to pull in the reliability commands, we issue the reliability command. All right, so that'll allow us to define random variables, performance functions, and run analyses, reliability analyses. So there's two random variables in this problem. First is the resistance, which I just used a tickle variable to store it. So this is the resistance value, or the mean value of resistance, and then also the mean value of load. Okay, so I just for no good reason, I set them as variables within tickle using the set command. All right. So after that, we can define two random variables. All right, they're both normally distributed. All right, we can go in and change the actual PDFs later, but just for demonstration's sake, we'll have two random variables that are normal. So the syntax here is the keyword random variable, and then a tag, distribution type, the dash mean, and then the mean value, and then dash stdv, and the standard deviation value. Okay, so random variable 1 is normal with a mean value pulled from the tickle variable. R, so $R references back to set R to 2000. Standard deviation is 135 units. Random variable 2, mean value of the load, this is normally distributed, referencing back to the tickle variable S, and standard deviation of 200. So a little more, or a higher COV for the load compared to the resistance. All right. And then so with the reliability analysis and most other optimization and sensitivity applications in OpenSees, everything's kind of linked to parameters. All right. So for each random variable, we want to create a parameter. All right. And to that end, we say parameter, and then the tag of the parameter, the type of parameter. This is a random variable, quote-unquote parameter, and then the tag of the random variable to which each parameter maps. So there's two parameters. They have the same tags as the random variables, but they're not. That doesn't necessarily have to happen. You don't have to have the same tags for the parameters and the random variables, but just for simplicity, they're the same here. Okay, so we define random variables. We define parameters that map to the random variables. Then we can use those parameters to define performance functions. All right, and I'll define 3 performance functions. They're equivalent. Some methods of reliability analysis are variant, some are invariant with respect to the limit state function. Okay, so these are 3 equivalent definitions of failure for the system. All right, so recall that where G is a performance function, if it's less than or equal to 0, that's a fail, and if G is greater than 0, that's considered a safe state. Okay, so performance function 1 is a linear function where we say basically G1 equals R minus S. All right, so resistance minus load. Okay, and that's to call out the random variables within our performance functions. We use a special tickle variable, set of tickle variables that call up our parameters. And in order to defer variable substitution to runtime as opposed to definition time, which is right now, we define each performance function within a string, and we want to dereference each parameter when we define our performance function. All right. But to defer that dereferencing to runtime, we use a / $sign parameter 1 minus / parameter 2. Okay, so this is storing a string that will be evaluated every time we need to evaluate the performance function and use the actual realizations of the parameters which are pointing to our random variables. Okay, hopefully that wasn't incredibly confusing, but I think it'll sink in at some point. So, second performance function is an equivalent definition of failure. All right, natural log of resistance minus natural log of load. Okay, so we'd say, using the built-in tickle functions, log, all right, say log parentheses, again, /$ to defer dereferencing to runtime, parameter 1 minus log of /$ parameter 2. Okay, and then the third function, G3, which is what OpenSees used to be known as many years ago, is R squared minus S squared. Okay, so we could use the PAL function there to do the square, or we could have just multiplied, you know, the par /$ par 1 times /$ par 1 minus /$ par 2 times /$ par 2. Okay, so there's many ways to define these functions. Okay, so these should all give the same definition of failure for an invariant method of reliability analysis. Okay, so should I pause here and see if there's any questions? Frank, I can't hear anyone, but perhaps Frank you can, and you can relay any questions.
Well, if anybody has questions, just enter them in the chat.
What?
You have to enter them in the chat window. Any questions, anybody? Doesn't look like there's any questions, Mike. Go on.
Okay. So the first method of analysis that I wanted to go through was FOSM analysis, or first order, second moment analysis. Okay, and this is a method that is not invariant to the definition of the performance function. So when we do FOSM analysis for these three performance functions, we'll get different answers, right, even though they are equivalent definitions of failure. But prior to running the FOSM analysis, we need to define a few things. First is how do we evaluate our performance functions? Well, we're going to use tickle to do that. So this highlighted command here indicates we're going to use tickle expressions to evaluate the function. So basically, everything up above, performance functions 1, 2, and 3, will get deferred or passed into a tickle expression. So imagine wrapping a square brackets and EXPR around each of these strings for performance functions 1, 2, and 3. That's how we're going to evaluate them. So we're going to let tickle do all the work. Okay, so it'll pull out the current values of par 1 and par 2, and then evaluate those mathematical expressions with those. Okay, then to evaluate gradients of the performance functions, we'll use finite differences, and the perturbation factor is 1,000. All right, so actually the perturbation is 1 over 1,000, even though the input is the reciprocal of that. And we'll start from the mean values of all the random variables. Right. So to do first order, second moment analysis, we type run FOSM analysis and then an output file, which will contain the results. All right, so there's more stuff after the script, or later in the script, but I'll just throw in a return there so that we don't go through the other calculations. Okay, let me make this a little bigger. So I'm running Linux here, but anyway, if you say OpenSees and then the file name is done down here, and run it, you see that there's a couple of little warnings specified that aren't really, that are pretty harmless. But then an indication that the FOSM analysis is running and that the FOSM analysis is complete. All right. So if we call out or view the file bar fosm.out, we'll see the analysis results. Okay. Performance function 1 or limit state function 1 at the top. It's the mean of the performance function, the standard deviation, and then the importance measures. All right. i.e. the ranking of the random variables and their influence on failure. And then for performance function 2, we see here that the results are different for the importance measures. I mean, they have the right signs. 1 is a load variable, 2 is a resistance variable. Wait, is that right? Yep. And then we have different values. All right, and this is coming from the lack of invariance for the first order second moment method. And here's performance function 3. All right. But as we see here, all the functions are very highly correlated. The failure, okay, so indicating that they're about the same. But however, we do get slightly different importance measures. Okay, so that's kind of a very basic method of reliability analysis, first order second moment. If we wanted to do form analysis, which is first order reliability method, which is invariant to the definition of our performance function, we'd have to define a few more things in our analysis, one being a probability transformation, which is how we get between standard normal space and the actual space of the random variables. Okay, and this is an iterative process, so we need a reliability convergence check. Usually the standard convergence check will suffice. I'll write some comments here. So this is the type. This is an absolute tolerance. This is a relative tolerance compared to the first iteration. And then the print flag. Like how much information do you want to see on the screen as the form analysis proceeds. This is very similar to the convergence tests for the standard finite element analysis within OpenSees. There's a flag indicating how much output you want to see. And then, so that's the convergence, and then the step size rule. How do we get through step through the form analysis? We can take fixed step sizes, which will work for this problem. So keyword fixed, step size is 1.0. And then we use a step search to find the design point, and we allow a maximum of 10 iterations out here, okay, to find the design point, which is the most likely point of failure. Okay, so after we define these extra objects for the analysis, we can run a form analysis, okay, and give a different file name to view the output. All right, so I'll just put a return there. So when we run this, it runs very, very quickly because it's a simple problem. But up here was the first order second moment analysis, and then from here on, the form analysis kicks in, and it's showing us the iterations for each performance function. So performance function 1 or limit state function 1 converges in 2 iterations because it's a linear function, just r minus s. And then this last value here is the distance from the mean to the most probable failure point or the design point. Okay, so we get to a beta value of 1.24 and some change. Limit state function 2 was the log r minus log s. It also converges to the same reliability index beta. It takes a few more iterations due to the nonlinearity of the function. Limit state function 3 also converges to the same reliability index, 1.24 and some change, in about 4 iterations. Okay, so this shows, as we know, the form analysis is invariant to our definition of failure. And then if we look at the output file, bar form.out, you see the results for the 3 limit state functions. Okay, so they start off at different mean points. All right. It's just because of the definition, but they all arrive to the same importance measures and reliability indices. Okay, 1.24 reliability index, that gives us probability of failure of about, what's that, 10%, or excuse me, yeah, about 10%. Same results obtained for limit state function 2 and limit state function 3. All right. So, oops. Get there, and yeah. Okay. And we can also, so that's the output that goes to the script. We can also, or excuse me, the output that goes to an output file. Within our Tickle script, we can also use kind of predefined functions to obtain output within our script that we could then manipulate for other applications. But beta form and then the limit state function or performance function tag gives the beta value or reliability index for limit state function with that tag. Okay, so we could set that in a Tickle variable, like set beta to be, its beta form is an array within Tickle, so we dereference it with a $, and then the tag of the limit state function that we want to get the reliability index for. I mean, they're all the same for these performance functions, but still it demonstrates some of the utility functions for manipulating and processing reliability results. So we can pull out within the script reliability index for limit state function 2. And if we wanted to get the probability of failure within the script, instead of searching through the output file, we can use a built-in function, get standard normal CDF, all right, with negative beta. So that's negative phi, excuse me, phi negative beta. Okay, so where phi is the standard normal CDF, mean 0, standard deviation 1. All right, so that's the mapping between reliability index and probability of failure. Okay, so if we were to run that, you can see here at the bottom of the script, this is the put-s statement from the script. PF, or probability of failure for limit state function 2, is equal to about 10.6 or 10.7%, or 0.1068, which matches the results within the file, which is right up here. Okay. So these utility functions like beta form and also gamma form and alpha for sensitivity measures or importance ranking can be pretty useful for running through scripts and processing results, as opposed to trying to parse these files and extract out that information. Okay, so I'll pause and ask Frank if there's any questions from the gallery.
If anybody has any questions, just again send in a chat message. So again, no questions. Michael, keep going.
Oh, okay. Can you ask if does everybody feel this is too basic, or?
Can I ask if everybody understands what form and storm is? What Michael's actually talking about? Everybody who knows what it is, can they say yes? And the only way to actually converse with us is through the chat. Everybody else is muted.
Okay.
Some people have been asking if they could talk.
Okay. So just keep going.
Yeah, keep going. We will be making the seminar available. We're making a video of it right now as the presentation goes on, and it will be made available. We will also make available this bar.pickle file for people to download and have a look at.
Right. Okay. So proceed.
Keep going, Mike.
Okay. So the next segment of the file does a Monte Carlo simulation using some of the utility functions defined within OpenSees for reliability analysis. Okay. So Monte Carlo simulation. All right. So form analysis gives us a kind of a linearized approximation to the failure domain, but Monte Carlo simulation can get around or for certain limit state functions, especially those with high nonlinearities, could give very different results compared to form. All right, although not for this problem, but I'm going to, for the sake of simplicity, show the Monte Carlo simulation. Okay. So basically, it's Monte Carlo is throwing darts at a dartboard and see how many land on the fail side and how many land on the safe side, and then take the ratio of fails to the total number of trials that you have. And this can be accomplished within Tickle loops or scripting within our Tickle files. Okay, so first we can set a variable for how many trials or how many Monte Carlo trials are we going to run. So I'm just making it 10,000 here, although more would probably be called for more complex problems. And then initializing the number of failure hits, right, which is initially 0. Okay, so we're going to run through 10,000 times, see how many times we fail for one of the limit state functions and how many times we are safe. Less than or equal to 0 is fail, and greater than 0 is safe. Okay, so a very basic for loop in Tickle, set I1, I less than number of trials, increment I by 1. Okay, so kind of the process here is to use is to generate random numbers within a standard normal space, and then transform those into the real space or the actual space of the random variables. Okay, so first we're going to build up a list, and for each trial, build up a list of random values within standard normal space. So this just initializes our list to be null. Okay, and then we say for each random variable, we could say for random variables 1 and 2, or we could say just go over all the random variables in the list of random variables returned by getRV tags. This getRV tags will return a Tickle list, a proper Tickle list of all the tags of random variables defined in your model. All right, so those are 1 and 2. Okay, but they could be 2 and 8, or 2, 8, 15, and 3. Whatever they are, this command will return a list of those integers. Okay, and we can use a for each loop to then iterate over that list. So for each RV from getRV tags, we can call up Tickle's built-in rand function, which just gives us a value. All right, so this returns a random number in the domain 0 to 1, all right, or random floating point value between 0 and 1. Okay, and then we can append to this standard normal list u, so lappend, list append, the Tickle function, to the list u. We call up the get standard normal inverse CDF function. Right, so that'll return a standard normal variate from a variate from the standard normal distribution based on the probability implied by the random number set in VAL or value. Okay, and that'll build up a list of for each random variable there'll be a standard normal variate added to this list for each Monte Carlo trial. So although the random variables are uncorrelated in this example, the way this is set up, it'll work for correlated random variables, in this case using the Natoff transformation, okay, which is what is invoked when we call transform u to x. So we pass in this list of standard normal variates, which is built up in this for each loop. It goes into transform u to x. So this will it'll call up the probability transformation object, which is in this case Nataf, and transform all the values in this list into a new list of values that are we'll store as x. All right. In some books, this is x and z. Some places you'll see it as x and u or u and z, but the u is the standard normals, and the x is the actual random variable values. Okay, so the next part is to update the parameter values that we defined up here, parameters 1 and 2, or random variables 1 and 2, is to iterate back through our list of random variable tags and say update parameter $RV, and then we index or list index into x with just a counter that we set here, IRV. Okay, so loop back through, pull out the list index from x, and then call the update parameter function in order to update the realizations of our random variables. Okay, and again, this is just one trial out of Monte Carlo, but it can work for any problem really. Then we can pull out this is probably a more elegant way to do this, but in concept, this is what we're doing. We can set x1 and x2 to be our random variables. We can call up the get parameter value, the parameter tag 1, parameter tag 2, and then evaluate our performance function. All right, using x1 squared minus x2 squared, or r squared minus s squared. G equals r squared minus s squared, which is one of our performance functions, I believe number 3 up top. Then if that variable comes out to being less than or equal to 0, we increment the number of failures by 1. And then we go through this loop, this process 10,000 times. And after that, we can get an estimate of the probability of failure as using the ratio of number of fail to the number of trials. All right, and be sure to use the double here, because Tickle does do integer division. So if you said just in fail divided by in trials, it'll always be 0. But if you convert the first argument to a double or floating point value, you'll get the floating point arithmetic. All right. I've banged my head a few times because my probability of failure always came out as 0 for Monte Carlo simulation because I left off the double part. Okay. So we can run this script again. It'll jog through the FOSM analysis and then the form analysis, and then down here, so this was from the form, and then here's the result of our Monte Carlo simulation. All right, it zipped through 10,000 trials fairly quickly, but we see we get about the same probability of failure. Okay, and of course, if we increase this to more trials, and we should, in theory, converge to something, all right, or not see a big, hopefully not a big change, but with 50,000 trials and the sequence of random numbers that are generated, now we get a probability of failure of about 10.4%, as opposed to the last one with 10,000, we got about 10.8 or 10.9%. So, but it's in the ballpark, or very similar to the form result. Okay. So one quick thing just to show you that the Monte Carlo will work for correlated random variables. We can introduce some artificial correlation between load and resistance. Right here, this is tag or RV1, RV2, and then the rho value or the correlation coefficient, say 0.5. And this is unrealistic because load and resistance normally would not be correlated, but just to demonstrate that this loop down here and this key part here, transform u to x, can handle correlated random variables. We'll jog through the same set of analyses with the correlated random variables. Okay. So we see from the form analysis that with this correlation, the probability of failure drops down to about 4.5%, and we also see the same result for the Monte Carlo simulation. Okay. So again, I think this is seemingly quite simple loop over here, but with these utility functions within OpenSees and reliability modules within OpenSees, you can do a lot with Monte Carlo simulation, as well as with the form analysis and other methods. Okay, so that's kind of the basics for form analysis, some correlation, and Monte Carlo simulation. I think you could pretty easily extract out this segment of code and apply it to just about any problem that you have, whether it's finite element reliability or just with dealing with raw random variables, such as this example here. These commands here are admittedly a little clunky and probably need to be updated. I mean, it could be nice to, instead of retyping the performance function, just be able to pass in a performance function tag, either 1, 2, or 3, and just say evaluate the function with whatever the current realizations of the random variables are. But we're getting there. But this will get the job done as well. Okay, so there's in the time left, I wanted to go through a kind of a finite element reliability analysis. All right, so I found a journal article from a couple of years ago on reliability analysis of steel frames with random properties. It's from the Journal of Structural Engineering. And they used OpenSees to do the analyses, and I thought it would be a good one to do reliability analysis on. Okay, so I'll just try to quickly highlight the key points here and go from there. Okay, so just like in the previous example, or any other OpenSees finite element analysis, we define the model builder, the number of dimensions, 2, number of degrees of freedom per node, 3, and then we issue the reliability analysis. So now the model builder here is necessary, whereas in the bar.tickle, it was just a placeholder. Okay. So, we of course don't have time to go through all the specifics of the model, but what it is a steel frame under gravity loads that's triggered to collapse under the gravity loads. Okay. So we go through the definition of fiber sections, all right, using uniaxial materials. We can call it the wide flange section commands, geometric transformations, co-rotational. So this example looks at both material and geometric nonlinearity. Okay, define our nodes. Okay, and then random variables and parameters. Okay, so here the random variable has the mean, standard deviation. The parameter, associated parameter, has a tag, random variable that it maps to, and then also the object in the finite element domain to which the parameter and random variable map. All right, so node 201, coordinate 1, which is the x direction. Okay, and then the next parameter maps to node 201, coordinate 2, which is the y coordinate. Excuse me. So yeah, this is x coordinate and y coordinate. Okay, so we have random nodal coordinates of several nodes, and then the element definitions, more nodal, random nodal coordinates. Columns, it's all standard beam definitions in OpenSees that I assume everyone has seen before. Define load patterns, so uniform loads, some point loads, and then we do a pushover analysis. I think this is just to get the mean response. And now we get into, here we go, defining random variables for the yield strength of the material. So we'd say log normal, or this is the common distribution for strength parameters, the mean value and standard deviation. And then we define a parameter. It's getting a little very tickle-centric, but kind of keeping track of tags and whatnot. It kind of behooves you to use expressions or arrays or other tricks within tickle when doing reliability analysis. But the point here is that this parameter maps to this random variable and also points to the yield strength of the element in the domain with the tag $ELE, right, which is just a simple loop over elements 1 and 2. All right, elastic modulus, so we'd say E is a parameter. Plastic hinge lengths, LPI, LPJ, depending on which element we're using. We can have plastic hinge lengths as parameters, random variables. And then the member depth, which usually has a pretty big influence on uncertainty, and probability of failure within a frame analysis. Okay, so then with the finite element reliability analysis, we need to define an integrator for the sensitivity as well as an algorithm for the sensitivity, which allows us to find the design point using direct differentiation method. So it's a static problem, so our integrator is static, and we want to compute the sensitivity at each step. Okay. Some analysis mumbo jumbo here, but key thing here is performance function. We have a limit on the x displacement of a particular node, or x direction displacement. So 50 millimeters is our limit. Okay, and everything in reliability analysis is meant to be a parameter. So the nodal displacement in question we can define as a parameter that can then be called up within our iteration for reliability analysis. So parameter tag is 1,000. It doesn't really matter what that tag is. It just needs to be something unique. And then node 201, one direction or x direction displacement, is the kind of the uncertain quantity or the quantity we're using to control or define failure. Right, so our performance function would be maximum displacement minus the actual displacement. So again, / $parameter 1,000. We'll defer dereferencing of this variable to runtime. All right, and a parameter 1,000 points back to the x direction displacement of node 201. All right, so that'll be queried during each iteration. Okay, so then down here we get into just all the parameters or modules for reliability analysis. Again, we see probability transformation, our reliability convergence check, function evaluator, right, which says every time we evaluate the function we want to evaluate, we should analyze a certain number of steps. Okay, so kind of like a pushover analysis, or in this case, a push down, because it's lateral collapse under vertical loads. Okay. Gradient evaluator is implicit, so this tells us this is the key for doing the DDM sensitivity for the gradient. Okay, it's implicit or finite difference are your two options there. All right, search direction, merit function check, these can all just pretty much be used as is, pasted into your script. Start point is the mean value of the random variables. And then step search is our algorithm. We'll allow it to go 20 iterations. All right, and then just like in the bar.tickle, we issue the run form analysis with an output file name. Okay, and then there's down here is some little slightly sophisticated tickle scripting to, well, first spit out the beta value, calling up beta form for limit state function 1, and then the importance ranking of random variables. Okay, so this goes through all of our random variables and spits out a ranked list of our importance measures, or a ranking of the random variables by importance measures, and puts it out to the screen. Okay, you could also fish it out of the industrial frame.out output file, but you can also manipulate using the utility functions added for reliability analysis in order to get that information. Okay, so I'll run this finite element reliability analysis, so OpenSees industrial frame.tickle. So we're using mean values of the random variables. Now we're going through our limit state functions. Of course, this is much slower than the bar example, just because there's a lot more going on. But we see that it's converging. It's getting to these values over here on the right are the distance from the mean point to the most probable failure point. And we do find the design point. Beta is very high, 5, which means we have a very low probability of failure. And then this next bit down here is the kind of the ranking of the random variables, like which ones have the biggest influence on failure at the design point. Okay, so this is beta. probability of failure is very small. So this is 5.076 standard deviations away from the mean on a standard normal distribution. All right. But anyway, random variable number 304 has the highest gamma value or importance measure, followed by random variable 303, random variable 601. So these are 304 and 303 are load variables. They have positive gamma values. 601 and 31 have negative gamma values, so they're considered resistance, as is random variable 602. But they all decrease in magnitude as we go down this list, which is what this kind of nasty-looking tickle loop was doing for us. It was sorting things out for us. Okay, and then we see that some of the random variables, 22, 501, 502, 551, 552, all have no importance. They're all 0, so they were not activated in the reliability analysis, or they had no influence on the on failure. For example, a yield strength of a member that did not yield, that would lead to a 0 importance measure or gamma value. Okay, so this industrial frame.tickle is also available in OpenSees repository. So for those of you who have SVN or you use SVN, if you look in OpenSees/examples/reliability, you'll see several examples in there. All right, so industrial frame.tickle we went through today, as well as bar.tickle, and there's several others. There's some that are from the CalRel manual, some standard test problems from CalRel, upon which the OpenSees reliability is based heavily. It's the CalRel implementation and functionality. So we like to make sure we can still run those basic examples, and so those are there. There's a portal frame. There's a couple of truss examples, a couple of class examples. I don't know if that was my class or Kevin Mackey's class. Let me see. Yeah, so this is from a class offered by Professor Kevin Mackey at University of Central Florida. But it's some more examples there that should work and can be used. Yeah, so steel frame.tickle, industrial frame.tickle for those of you who are looking for beam column type of reliability analyses. Those are there. I plan to add some reinforced concrete frame examples in there. The steel frame is of course steel frame, and industrial frame is also a steel members. Okay, reinforced concrete's a little more involved, but certainly doable with the capabilities and the OpenSees reliability. Okay, and again, these files are available in this directory, OpenSees/examples/reliability. All right, so I guess at this point I'm done. I think we can open to questions, or if you just want to send.
We have a couple of questions come in.
Yeah.
While I have you here. From Sine, would it be possible to do something like this with 3-floor wall building?
With what?
30 pairs of earthquake records, parametric study. I'd like to see how much my shear demand varies when I run the 30 pairs of earthquake records.
I think with the form so the time variant sorts of problems are much more difficult to solve. Form analysis wouldn't really be applicable to for dynamics or nonlinear dynamics, because when you change parameters, you could have peaks at different times, and things become a little messy. And there's more advanced methods like outcrossing analysis that would need to be done, those methods are still under development. There's also the Telem analysis, which is marginally functional within OpenSees at the moment. But yeah, with dynamics, excuse me?
I guess the surefire way to do it was like a Monte Carlo.
The shear power?
Surefire way to get answers would be to tell them to use a Monte Carlo.
Yeah, I mean, Monte Carlo might be the one thing to look into. You know, if you're just looking at, you know, shear force being above or below a certain threshold, and you don't care, like at what time that occurs within an analysis, then yeah, Monte Carlo can certainly work. But you know, you're going to be running a lot of simulations, 10,000 or 100,000 time history analyses, and then, but it's embarrassingly parallel, and you know, could be forked out pretty easily to multiple machines.
Another question is, you did this for a 2D frame, would it be possible to do it for a 3D frame? Frames in both directions. You've demonstrated this for a 2D frame, would it be possible to implement this with 3D building with frames in both directions?
Yes, that would be possible. Some of the only thing is some of the parameter and sensitivity parts for the gradient evaluator being implicit as opposed to finite difference. Some of that functionality may not be implemented across the board for all of the 3D elements, but yes, I mean, it is that functionality is there, and yeah, it's a matter of what at the element level, you know, what's been implemented.
I guess how do they know at the element level what elements work and which don't?
Well, there's the Frank McKenna answer, which is read the source code. It's all self-documenting, right? But there's if you really want to dig into the source code, there's two methods that you need to look into for the elements that you're using, and I'll try to bring that up here. So, like, what 3D element are we talking about? I guess maybe we just do the force beam column. So if we look at force beam column 3D.cpp, let's see, tool options. Wait, edit text properties. There we go. So if there's the set parameter is one method that you should look into first. So for the parameter command, in order to update values, or identify and update set parameter is an important one. So make sure with the elements you're using, search the source code for this set parameter method, and then see what are these strings. So rho, like the mass density for the element, is one possibility. Section response is another. Section response. The integration, like plastic hinge links or whatnot. Looks like that's all been enabled for this element. Okay, and then also update parameter, but that is for this particular case. It just the set parameter just gets passed on to the beam integration or the sections. Okay, so then you have to dig down into, well, if I'm using fiber sections, material section, fiber section 3D, look for set parameter there. All right, and then okay, material. It'll look for material properties or integration, like the section integration, cross-sectional dimensions and whatnot. So then you have to dig down into, well, I'm using hardening material or steel 01 or whatever, and look for set parameter there. Okay, it'll take sigma y, fy, e, kinematic hardening, isotropic hardening moduli, and then also the update parameter there. And then you should see for the materials, like if this get stress sensitivity is implemented, which it is for this material, then you're probably good to go. But if these parameter or sensitivity methods are not defined within the models that you're using, then you're relegated to well, if the parameter thing doesn't work, you can't even, if set parameter and update parameter are not implemented, you're kind of out of luck. You can't even do Monte Carlo simulation unless you like did it at a higher level and wiped your model on every trial and just to handle all the randomness yourself within a script. And then if the get stress sensitivity is not implemented, then you can't do DDM or implicit type of gradients. But at a minimum, you need the set and update parameter to be implemented, because then you can do finite difference calculations and Monte Carlo updates pretty easily. So unfortunately there's no master list of what is sensitized or parameterized, but there probably should be, right? So let me write this down: master list of what is available for parameters and sensitivity. Okay, but the long answer is, or the short answer with a long trail of searching, is to look in the source code for those parameter methods and sensitivity methods.
Can you read the other questions, Michael? Or do I need to keep reading them to you?
Say that again?
Can you read the chat questions, or do I just keep reading them to you?
I can't. Yeah, I can't.
Click on the chat there. Join one.
Oh.
There you go.
Okay. So where were we? Okay, 3D building. Sign up. Yeah, I'll share the example files. The higher trial is more appropriate for reliability now. Like the higher number of trials. This is from Koktong Tan. I'm not sure what the question. I mean, more if you're talking about Monte Carlo trials, yeah, higher number is usually better. So, I mean, you should converge to an answer with the higher Monte Carlo trials, but you don't want to do billions, but 10,000, 100,000 is usually pretty good. From Sunai Kim, when you plan on adding the RC example, hopefully within, I have a student working on one as we speak, and so hopefully that'll be soon, and we can get it posted to the, or uploaded into the repository, and then we can post on the message board about its availability. From Toby, can the output be used for building fertility curves? Yes, it can be, and how you do that is up to you. But you can extract out. You can write scripts that extract out the probability of failure for different performance functions or different levels of intensity, and then kind of build up fragility curves that way. For Rodrigo Estroza, any documentation or manual for reliability and response sensitivity, DDM analysis of displacement-based and force-based elements. Well, there's journal papers on it. I think there's some limited sensitivity documentation available on the OpenSees wiki, not written by me, but by other researchers. There's some previous OpenSees days workshop presentations where this is documented. So I may look in the OpenSees days 2012, perhaps, or maybe 2013. There's some documentation there.
There's also, if you have questions on the reliability, you might point out the place on the message board for any questions.
Yeah, so there is a separate forum on the message board, OpenSees. If you go out of OpenSees users, there's one for reliability analysis. Is my screen still visible?
It's fairly, but it's enough.
Okay, but in here there's a few questions have been posted. This is a relatively new forum, but you can ask specific reliability questions there, so it doesn't get lost in the shuffle of help my model does not converge, or help OpenSees crashes. What do I do questions that are in the OpenSees.exe users forum. So that was another resource. If we go to OpenSees Days 2012, or let's see. Yeah, is there a 2011 one? Yeah. Yeah, so OpenSees Days 2011. I know this is kind of small on the screen, but there's a couple of presentations there. One by Professor Jack Regan on kind of some mostly theory behind reliability and sensitivity within OpenSees, and then also one by me on using it within OpenSees, or by myself and Kevin Mackey